When we have multiple resonance structures drawn for one system, one molecule, we know that they combine or they blend into what we call the hybrid structure of the actual compound that we can study in the lab experimentally. In some cases, you can find that all resonance structures contribute the same, although the most common scenario by far is that not all resonance structures will contribute equally to that hybrid. Here we're going to have a few rules that we're going to discuss, listed in order of importance, that will allow us to determine the most significant resonance structure for a given compound. In other words, the major contributor, minor contributor, insignificant contributors, etc. Rule number one. The most significant resonance forms have the greatest number of field octets. Right? This just makes sense. If you can have your octet, that gives you greater stability, so nature actually prefers that quite a bit. Here we have two potential structures. The one on the left has less significance when figuring out the hybrid because the carbocation doesn't have a full octet. The structure on the right becomes a lot more important, becomes a majority contributor because it actually does have octet rule. Now we follow the octet rule. Rule number two, the structure with fewer formal charges is more significant. So the less spread out, the less polarized the system becomes, these formal charges become, then the more stable the entire system overall is. If you look here, we have three structures. The most significant is going to be the one on the left, and the least significant will be the one on the extreme right. The first two structures both have full octets, but the first one has fewer formal charges. So that means that we go from most significant, somewhere in between, very little significance at all. If the compound has an overall formal charge, then we focus only on drawing resonance forms that show the delocalization of that charge. So basically how it moves throughout the structure to give us that hybrid. Here, for instance, we have all these charges spread out. This doesn't really make sense. I wouldn't expect this to show up in any experiment, any scenario, simply because of the way the charges are distributed. Which leads us to rule number three, actually. A structure with a negative charge on the more electronegative atom will be more significant and vice versa. What that means is that if I have a negative charge and I have to choose, let's say, between carbon and oxygen, for example, then oxygen is much more likely to carry that negative charge because it's more electronegative than carbon will. On the other hand, if there is a positive charge, then I would expect carbon to be carrying that charge instead of oxygen in that hypothetical scenario. In this structure that we have here as an example, we're going to default to rule number three here because more than one structure has all atoms with a full octet and they have the same number of formal charges. Now it becomes a matter of where are these formal charges localized. Again, we pick the more electronegative atoms will most likely carry those negative charges, and then vice versa. Rule number four, resonance forms that have equally good Lewis structures are described as equivalent and contribute equally to the resonance structure. The classic case would be the carbonate ion, where you have that negative distribution among all of the oxygen atoms, and then the positive side of that molecule will lay on carbon. That makes perfect sense from the point of view of charge distribution. So we can't really assign preference in any of these three hybrids, so we say that they're all equivalent contributors. Pi bonds and formal charges are often more spread out than bond-line structures can imply. Consider, for instance, this drawing we have here, the resonance stabilized allyl carbocation. In this case, the pi bond and the positive charge are inadequately described by a bond-line structure. So in other words, we draw this very neat, very elegant, double bond here, positive charge here, vice versa, but in reality it's more messy. So that charge gets distributed a lot more throughout the structure, and so is that pi cloud that will form the double bond. If all of the carbons have unhybridized p orbitals, then all three of them overlap side by side. In the example we just saw, all three overlapping p orbitals allow the electrons to move throughout the overlapping area. And so we say the molecule has resonance, and what we mean by that is that the electrons are delocalized. They actually travel through the molecule. So it's not as simple as just drawing two lines and calling it a day. From a molecular point of view, The three unhybridized p orbitals overlap to form three new molecular orbitals. These 2 pi electrons occupy the lowest molecular orbital, which is the bonding molecular orbital, right here, the bottom one. And in the case of the allyl carbocation, it has a charge of a +1. If it actually gained an electron, it would go into the non-bonding, so it would have to jump that third electron. The symmetry of the non-bonding molecular orbital suggests the cationic charge is spread out to both ends of the 3-carbon chain, not just one carbon atom drawn with the positive charge. So it's much more messy than the drawings we've been doing would lead you to believe. That's an important point. You have to keep that in mind. So how can we use bond line structures to accurately describe the positive charge on the allyl carbocation? The pi electrons can exist on both sides of the middle carbon, so we can draw two different resonance structures to represent the compound. Always keeping in mind, like I said, that the actual structure is going to be neither of these. It's going to be something of a hybrid. No? The resonance arrow and the brackets indicate these structures are describing just the one compound. Ideally, we would draw something kind of like this, with that dashed line, partial positive charge on both sides, and this would represent a little bit more accurately what we see in the lab. However, this is not your typical Lewis or even bond line, let's say, nomenclature or system, so we usually stick to this guy right here. You will, however, see in some cases where we're describing mechanisms, we're describing stationary states, intermediates, things that are short-lived, but it's very important that we get them right. You will see drawings such as this one, and as you can see, they are representing partial bond formation, partial bond breaking, etc. The main point of all of this, the reason I'm saying all of this, is because of this point right here. The resonance structures are not switching back and forth, it's just one stable, and it exists, and that's it. Delocalized electrons are more spread out, thus lower energy, thus more stable. So that's the whole reason why it makes sense in nature to have this type of structure instead of having that double bond switching back and forth. It's just much more stable this way, and nature likes stability. Localized electrons, on the other hand, when we say localized, they're placed somewhere specific, so that means that they're not in resonance. Delocalized electrons are most definitely in resonance and therefore more stable. To be delocalized, a lone pair of electrons must be adjacent to an atom with an unhybridized p orbital. The lone pair on the nitrogen here, for instance, is delocalized because it is next door to a carbon atom with a p orbital. This guy right here. In one of the structures, the nitrogen is sp3 hybridized, and in the other, it indicates that the nitrogen is sp2 hybridized. So which is it? Well, the lone pair is delocalized, which is only possible through overlapping p orbitals. That would suggest that the nitrogen has to be sp2 hybridized. A lone pair by itself does not participate in resonance if it cannot overlap with an adjacent p orbital. It is a localized lone pair. It's important we make this distinction, as the chemistry, the reactivity, and all other properties that we study are directly affected by whether a pair of electrons is localized or delocalized. Here, for example, we have pyridine. This molecule, the lone pair in pyridine, can't really overlap with p orbital of the adjacent atom. Therefore, it is a localized lone pair. It's important, right, to keep in mind these points. Don't assume a lone pair is delocalized just because it is next door to a pi bond. Generally, you can assume that when an atom possesses a pi bond and a lone pair, they will both not participate in resonance. It's going to be either one or the other. And as always, if there is no p orbital next door to the lone pair, then it will most definitely be a localized system, a localized entity, a localized lone pair of electrons.